So now let's work through some of these stoichiometry problems. Now, before you watch this video, you should have completed these problems, or at the very least, started to try them. So what I would recommend here, and this is something I would not just recommend here, but for many of these future exercises, especially as concepts get more difficult in this course, is you should always try and work through all of these problems before you come and watch the videos with the solutions. If you find that you're struggling to get through the problems at all, then what I would recommend is maybe come and watch the solution to the first problem or the first part of the first problem, and then stop the video and come back and try some more of the problems, and then come back and watch more of this. All right, how do we start one of these? Well, we know the first thing that we need to do is we always need to balance the equations. And that's always your first step. And so now what we're saying is we started with 21.3 grams of nitrogen. How much ammonia could we form? So this is very much like some of the practice ones we did. 23 grams of nitrogen times 1 mole of nitrogen over the molar mass of nitrogen, which is 28 grams. We will then use our mole to mole conversion. 2 moles of ammonia are made from 1 mole of nitrogen. And then we use the molar mass to convert back to grams. So 17 grams of ammonia is equivalent to 1 mole. And then we just do our math. And we find that it's 25.8 grams of ammonia. Now in part B, we're trying to determine how much of the starting materials we need to make a certain amount of product. And specifically what we're looking for is 100 grams of ammonia. So here we're just going to be working backwards. We're going to take the amount of ammonia that we need, 100 grams, and work our way backwards to the amount of each of the starting materials. So that's going to be 2 separate calculations. Both of them are going to start by converting grams of ammonia to moles of ammonia. Then we're going to go from moles of product back to moles of starting material. So let's do nitrogen first. And in fact, it's going to be exactly the opposite sequence of what we did above. So 1 mole of nitrogen is needed for each 2 moles of ammonia. And then 1 mole of nitrogen can be made, or is equivalent, its molar mass is 28 grams of nitrogen. And so we get that to make 100 grams of ammonia, we need 82.35 grams of nitrogen. How much hydrogen do we need? Well, the safe bet is that we need 100 minus 82.35 grams, or 17.65 grams. But let's check that. Let's go step by step through the process. 100 grams of ammonia. Again, we'll convert that to moles. Then we'll go from moles of ammonia to moles of hydrogen. And finally, from moles of hydrogen to grams of hydrogen. And we find, just as we expected, that we need 17.56 grams of hydrogen. All right, let's go on to our next example. Here we're looking at octane. So in other words, as you burn gas in your car, how much water does it produce? So we need to balance this. I'm not going to go through the balancing. We've actually already done this one. And we know that the coefficients are 2, 25, 16, and 18. So let's say we have 100 grams of octane. We're going to divide that by its molar mass to give us moles of octane. That's 1 mole over 114 grams. Then we're going to go from moles of octane, which is 2 moles, to moles of water, which is 18. And then from grams of, or moles of water, to grams of water, 18 grams. And we get that burning 100 grams of gas, or 100 grams of octane, forms 142.1 grams of water. Now, does that seem like a lot? Well, let's put this in a different context. Now, instead of burning off just 100 grams of octane, what if we burned a whole tank? So 15 gallons is a pretty typical size for a gas tank. So what if we burned 15 gallons of gas? How much water do we make? Well, the first thing is, clearly we're not in a unit that's going to help us do this calculation. If we want to do mole calculations, we need to be in grams, not gallons. So we're going to have to start out by converting. So 15 gallons times 3.79 liters over 1 gallon. Then we're going to go from liters to milliliters. The reason we need to do that is our density is in grams per milliliter. So 1 liter is 1,000 milliliters. And now we can convert to grams using the density. 0.073 grams of octane is equivalent to 1 milliliter of octane. So let's calculate that. And we get 39,965 milliliters of octane. So now we're going to need to convert that to water. So 39,965 grams of octane times 1 mole of octane over 114 grams of octane. Now we need our moles to moles conversion. 18 moles of water over 2 moles of octane. And finally, 18 grams of water over 1 mole of water. And we get that by burning 1 tank of gas, we form 56,793 grams of water. Probably a lot more than we would have expected. Now we're going to start getting into more situations dealing with limiting reactants. So right here, we are saying we have 100 grams of HCl and 100 grams of sodium hydroxide. So how much sodium chloride can we make? There's two things we should be very careful of. First of all, the answer is not 200 grams. We can't just add these together. And there's two reasons for that. Our two starting materials don't have the same molar mass. And so because they don't have the same molar mass, we will have different moles of each reagent. And that means one will be limiting and one won't be. The second thing is we're forming two products. And so that whatever material does react is going to be split between two products. So there's no way we could get exactly 200 grams here. But we're going to break this up. So how much sodium chloride could we make from 100 grams of HCl? Well, this is the same calculation we've been doing. We can take our mass of HCl and convert that to moles of HCl. Go from moles of HCl to moles of sodium chloride. You'll notice I didn't say anything about balancing this equation, and the reason is that it's already balanced. And then we can go from moles of sodium chloride to grams. And so our 100 grams of hydrochloric acid are enough to make 160.3 grams of sodium chloride. Now we do the same thing for sodium hydroxide. The primary thing that changes here is that sodium hydroxide has a different mass from hydrochloric acid. The other thing that changes is the denominator here is moles of sodium hydroxide instead of moles of HCl. And then our third conversion factor ends up being the same because at this point we're going moles of sodium chloride to grams. Calculate that, we get 146.1 grams. Of sodium chloride. So what we're saying here is that 100 grams of hydrochloric acid is enough to make 160 grams of sodium chloride, but 100 grams of sodium hydroxide is only enough to make 146.1 grams of sodium chloride. So what's our limiting reactant? Our limiting reactant is the sodium hydroxide, because that's the one that lets us make less sodium chloride. So if we had exactly 100 grams of HCl and 100 grams of sodium hydroxide, how much sodium chloride could we form? Well, it's the lesser of the two amounts, 146.1 grams. Finally, our last question on this sheet, we're going to work backwards. So I've given you an amount of product, and I'm asking you to determine how much of each of the starting materials that we need. So here, again, the equation is not balanced. We'll need to do that. But otherwise, this problem is just like all the others we've done. The only difference is that we're going to work backwards. So 123.45 grams of phosphoric acid. We're going to divide that by the molar mass of phosphoric acid. Use our coefficients to do our moles to moles conversion. So 4 moles of phosphoric acid go on the bottom, 1 mole of P4O10 on top, and then we need the molar mass of P4O10. Molar mass is 284 grams. And we find that to make 123.45 grams of phosphoric acid, we need 89.44 grams of P4O10. Now, how do we find the amount of water? Well, we can do the same thing, just changing our second and third term, or we can do this one the easy way. 123.45 grams. We know that 89.44 of that comes from P4O10. Therefore, the rest of it has to be from the water. And so the remaining amount is 34.01 grams of water.